Cheers, Dylan. Yeah, thanks for that. So yeah, the idea behind this talk is just an update on some previous work, which has covered simulating radar profiles for monitoring of glaciers. So the outline of the talk is as follows. I'll give sort of an introduction of why you might want to do this. Why do we need a simulation tool for this? Why can't we even get the data ourselves? The approach that we're taking to this simulation and sort of the justification behind that. Some of the modifications that I've had to make to this over the last month or so to allow for different model types. So this is sort of the bulk of the bulk of the talk focuses on, and then I'll touch on some results towards the end. So for those unfamiliar with the sort of glacial realm, this is a cartoon of an ice shelf. So we have the ice on the left-hand side of the screen is flowing from the continent out into out towards the sea over here, and where the ice meets the sea, it becomes a float. And then we have all these sort of interesting things that glaciologists and oceanographers are interested in at the base of an ice shelf. So we have fresh water that melts through the ice column and escapes through the base of the ice shelf. We have crevasses that form at the base of the ice shelf that can weaken the ice shelf or might provide points of fracture, and melt that occurs underneath. So as well as melt occurring at the top where surface air temperatures are getting warmer, if we also see melt at the bottom, then obviously that can enhance the rate that these ice shelves are shedding icebergs or carving into the ocean. So that's sort of why this is of interest. So the way that I'm interested in studying ice shelves and ice masses in general with radar, so whether that's ground-based and we situate the radar on the ice shelf, or whether we're using an airborne or even spaceborne radar to monitor changes in these features, changes in thickness, changes in location, or to identify whether we have any of these kind of features within an ice shelf, and then what effect that has further down the line. So why do we need a simulation tool to simulate these sort of radar surveys? Well, they provide test data sets for any of the processing that they're going to do. And the reason we need to do that is because collecting the real data is it's expensive, it's unpredictable. Orchestrating a field campaign to collect this data in the real world is, not something you can do sort of, every week. So in order to get the sort of representative data of what we might expect, simulation tools are a really powerful option to be able to develop the processing routines. So the broad scope of my PhD project is to look at synthetic aperture radar, imaging of the base of ice shelves, ice sheets, and ice masses, and this will allow us to collect these sort of test data sets so that we can verify our SAR approach. Inverse modeling is also another application for these kind of simulations. So if you have collected some data, you have a strange signature in your data set, and you're not sure what physical feature has given rise to that, you can use this sort of inverse modeling approach to say, okay, well, I suppose inverse or forward modeling approach, say, well, it could be this. What does the radar signature look like? Okay, well, that matches up what we're seeing. Or if we change these parameters, can we get something that looks like what we're seeing? And that can be used to explain some of these sort of peculiarities that you get arising in radar signatures from conducted in radar surveys. And then also the need for this simulation tool is that the existing approaches we have are, I've put in quotes, unsuitable, that they're applicable, you can use them, people do use them, but they're computationally very expensive. So if there's a way that we can reduce the computation effort required to generate these sort of synthetic data sets, then that's also a good thing, and makes the tool more widely available to the to the scientific community. So what are we trying to achieve with these simulations? So I've put these 4 points here. So first of all, we're trying to provide a sort of two-dimensional snapshot of a ice mass, so whether that's an ice shelf, ice sheet, etc. So some of the most common features that you observe in radargrams of ice shelves, ice sheets, are layers within the glacier. So that was one of the key things that we wanted to be able to introduce, is to sort of represent these layers, whether that's just the surface, the bed, and maybe some internal layers that can occur or arise from changes in density, acidity, etc. within the ice. The next thing we want to be able to do is define our radar parameters. So what frequency, center frequency, bandwidth. For this, these are all for an FMCW style radar. So what's the chirp duration, or equivalent of a PRF for a pulsed radar? If we change our sampling rate, how does that affect the response that we see as well? So we want to be able to sort of define all of these radar related configurations, and then from that generate a sort of complex phase history for a bunch of profiles along this model. And then in doing all of this, we want to keep the complexity, the computation time below that of the full three-dimensional model equivalent. So at sort of this point, I'll sort of try and make the argument that the reason we're cutting this down to 2 dimensions from 3 dimensions is that we're interested in geometry that is changing over a scale of sort of, you can see here, tens of kilometers, and here we have the scale sort of much exaggerated on the y-axis of only a kilometer deep. So there's not too much variation necessarily looking into the image. So if we're interested in these geometries which vary on the scale of kilometers in length, and we're sort of interested in features that are happening along the profile length, and assuming that there's not too much change in and out of left and right of nadir of the radar as we're looking down into the ice. So some sort of features to point out there. We have some glacial layering, as I mentioned. We have this basal reflection. That could be from bedrock. It could be from where the ice and the sea are in contact. That might not be that well defined either. There might be some sort of blurring between those regions. And then we have sort of other features as well that we're able to identify. So as I've mentioned, we take this sort of layered approach. So we say, okay, at the surface we have some air. We might have some layers of ice with different permittivity, different density, that we can define different loss characteristics, etc. And we define these by these sort of line or piecewise kind of lines across our model domain. So we assume that if we have a layer across our model, that layer extends infinitely downwards until it meets another layer. So we have this first layer which extends down until it meets this second layer, it's onwards until it meets our bedrock, etc. And then when we reach our bedrock, we don't know what's beyond that, so we're going to assume that it just continues indefinitely. We're not interested in anything below the that final interface. And yeah, so then, like I've said, we also needed to find the radar configurations. That's whether it's the transmit, receive positions, etc. So then to get the radar response, the first thing we want to be able to do is to get this in the time domains. This is the deramped FMCW response. So after multiplication with the transmit signal of the receive signal, so this sort of low, well, hopefully low frequency kind of signal, and we do that by summing the point response for discretized targets along each of these layers. So we say we have a layer. Can we represent that as a series of point targets that are closely spaced? And if we do that, what's the and we do that for each layer, what's the response that we see? So we need to know the travel time from the transmit and to this point target back to the receive target. And to calculate that, we sort of take into account refraction effects between each of these layers. So that's going to be have quite a significant impact, certainly in glaciology, where you can have sort of quite high contrasts between the different dielectrics that you have in your model. You could have you'd be transmitting an air, and you could have sort of fresh water, salt water with sort of permittivities on the order of sort of 80 or so. So it's quite a large scale there to see some sort of strange refraction effects occurring. But even the refraction between air and ice, which has the permittivity of about 3.1, 3.2, you can see some sort of significant refraction occurring there, and that will have an effect on the radar data that you see. So in terms of sort of how this looks, or what the model chucks out, you can see it's picking all of these discrete points on this model here. We've got some water down the bottom, and then we get our deramped FMCW signal, and we can do the standard FFT processing on that to retrieve this range profile. So you can see here the response from the surface, from the this glacial layer, and then from the basal layer at the bottom, and that will have some sort of mixed response here as well, from this sort of difference between the bedrock and between the water layer. So this looks okay, it looks like it can work, but what were the limitations of the approach that we were doing as it was? Well, first of all, the layers were assumed to be parallel. We assumed that the refraction that took place was sort of locally parallel. We weren't using, so if we had a layer like this at an angle or with a step, we sort of take the sort of average position of that layer to compute the refraction through the model. So you're sort of limited to quite simple geometries with this. And then obviously that can lead to a difference in your true ray path, where you would expect it to these rays to bounce, and the reflected ray path, which is if there's a difference in the travel time between those two, then that will feed back into when you're doing your processing. If you're trying to account for any of these refraction effects, there'll be an error added by the simulation in that process, in that approximation being made. The second limitation was that we actually couldn't represent models here with what I've called a zero height between layers. So we define the ice layer, and then what we sort of, I'll try and draw this on here, but sort of have to imagine that, if I can find my pen, that there are two layers here. We've defined one layer like this, we've defined another layer like that, and there's this sort of section here where they overlap. Between them is zero or nearly zero. We weren't able to deal with that before. You'd be trying to solve this sort of infinitesimal refraction between those two layers. So for geometries like this, which represent the grounding line, if you think back to that ice sheet cartoon I had at the very beginning, where we see the seawater coming out from underneath the ice, that's obviously a geometry of interest to study, so we need to be able to represent those. So as I've said, they're useful for representing various geometries. Another one of those is this sort of basal channel geometry. We could also represent things like ice lenses, which are sort of solid inclusions of ice within the firn. So that's sort of the compacted snow at the upper layers of a glacier. We can get ice lenses occur, and these will also sort of distort or introduce scattering into your radar surveys that we're now able to represent. If we can represent these sort of zero height layers, we can have so I suppose an ice lens might look a bit like sort of a layer of ice that appears, bulges out, and very simply like that. So then we have some sort of more dense ice between snow either side. So how does the zero height approach work? How do we actually take this sort of cartoon idea of these layers that we've defined, this geometry, and how do we then calculate the propagation delay and the attenuation and all of the characteristics of these rays that we're bouncing from or sending from the transmitter to these point targets and back to the receiver in order to build up our radar response. So the first step is to define your model. We define these layers. So as I said, we can have our air layer. We'll then define a seawater layer. So that's the next layer we define. Then we can define our bedrock layer, and we have these sort of different propagation media. They need to be sorted by elevation. So that's the first step. So we can identify these different layers. We have air, ice, bedrock, and our seawater. I obviously can't number things correctly, so 3 and 4 should be swapped around there. And then we need to identify from these layers where two or more layers might meet, what interfaces do we actually have. So at the top here, we have an air-ice interface, which will dictate things like our the reflected power or the reflection coefficient of that layer. You know, it might introduce a phase change as well if, for example, if the material had a loss associated with it, and there would be a phase change associated with that interface as well. And in the zero height model, the difficulty is sort of identifying trying to discriminate between the ice bedrock, ice water, and water bedrock interfaces. So we can iterate through all of the layers we have. We calculate their height. We look for the points where the height between them is equal to 0. Really, you don't have to specify it to be 0. There is a tolerance in the code that you can specify the layer to actually say anything less than 1 meter. We're just going to assume is close enough together. So there is the scope to sort of introduce a bit of tolerance into that, or say approximate this as being almost these two layers meeting each other if you only want it to be very thin, or not account for refraction effects between the two layers at that point. So yeah, step 2, we've identified those interfaces, and then the step 3, we now want to sort of turn this into a graph, or a directed graph. So each of our propagation media, so that's the air, ice, seawater, and bedrock, become a node on our graph, and then we can connect these nodes based on the interfaces that exist between these different media. So we know we can go from air to ice, from ice to water, or we can go from ice directly to bedrock. And then we know that from from the seawater, we can also go to the bedrock. So we have, from our 4 nodes on the graph, or from our 4 nodes, we can sort of construct this graph. You can represent that in matrix form. These values could be representative of the actual. They could be representative of distances, or average distances between these interfaces, or changes in permittivity. There is scope to make use of some more use of that. But at the moment, I just assign a unitary value, whether those nodes are connected or not, and then we're able to traverse that matrix to find these unique paths. So first of all, we can go from the first node to the second node. We can go from first to second to third, first to second to fourth, first, second, third, fourth. So we're able to identify that there are 4 unique paths from the first node to each subsequent node from that. So that's important for then when we're going to split these interfaces into segments. So here, this is a simple case. We have 1 segment per interface, so there's not too much difficult to do there. If we had a model like our Basal channel model, then the only difference is if our zero height layer occurs in the middle of our model rather than towards one edge, we might find that for our bedrock interface, we split that into two segments here. We have to just treat these two segments separately for when we are going to calculate the refraction from the surface to points on that layer, or sorry, points through that interface. So as I said, split those up into segments. And then finally, for each segment that we've identified, so we've identified the interfaces, we've identified the propagation media within that, we've identified the segments that make up the interfaces, and then finally, for each segment, we split this up into these point targets. So obviously, we're turning something that is a linear feature into points, but I'll come to how we deal with that in a moment. But each point is assigned a length. It's assigned a normal orientation of the direction that normal to the direction that the line is pointing, and then we also store the position of each point. So it's not just a point target; it also does have a sort of orientation and a length that we use to calculate the RCS of each of these point targets. And then we'll also need to determine, of course, the upper and lower permittivity of each interface. So here we'll have ice and water, and then here we'll have ice and bedrock. So that will determine the sort of reflection characteristics. But that the determination of these material properties above and below sort of follow quite nicely from the graph. You can, if you select your subscript on the graph correctly, then you can sort of quite easily pick out which material is above and below you. So having that graph sort of serves multiple purposes. It was also allows us to make sure we're looking at the right material above and below to do the reflection calculations. So to go from, we've generated our model, so now we need to calculate a range profile for a position that we're defining our transmitter and our receiver. So for each of those interfaces that we've identified, we want to sum the point response from all of the point or line targets that we have along that interface. So we calculate the path from the point target through any intermediate layers to that interface. Each target, we're going to find the transmission path constrained by Fresnel's law and Snell's law. So that's finding the minimum travel time constrained by Snell's law. And then we're going to calculate the attenuation that our array experiences and sum those complex point target responses, and ultimately sum those for each layer within the model. And then we have our deramped FMCW signal at the end. So that just the geometry here for finding that constrained Snell's path. As long as we know the sort of normal of each intermediate segment, then we can sort of use, so all this code is written in MATLAB, so we've used the function minimize as a constrained function minimization function, fmincon, to minimize the travel time for each of these segments based on, or sort of constrained by Snell's law, and then we do that for the receive path as well. And obviously doing this numerically, nothing's going to be exact. So there's a programmable tolerance to say, okay, well, if we're sort of meeting Snell's constraint within the default values 0.001, but that's up to sort of, that's been determined sort of experimentally, but there is, you could change that and you would find that perhaps actually you had fewer rays being found within your model. Or you could make it larger and you'd find that actually then you were starting to see slightly more non-physical path being represented. But again, that's been programmed in. What it does mean is that more segments you have per layer, this whole process will exponentially increasing in complexity. So for a geometry like this basal channel, where we want to represent this nonlinear kind of semicircle, we'll have to split that up into smaller sub segments, and to represent the semicircle faithfully, obviously the more subsegments we need. So that's another trade-off that needs to come from the designer of the model of what's an acceptable complexity versus the computation time, or versus the sort of accuracy we want to see in this in the refraction response being calculated. So it's not just for these sort of final segments. Also, if you have a layer in the middle with multiple segments and then another layer with multiple segments, you're going to have to find the refraction path for each of the first layer segments through each of the previous ones, then next, then above. Then the more layers you add, obviously, the more layers that you're having to go back and trace each segment with. So yeah, it can become quite overhead quite quickly. So the idea is to try and keep the geometry relatively straightforward. In terms of the attenuation and link budget, we then have this is our sort of link budget equation. So we have the transmitted power. We then account for any intermediate layer. We calculate the Fresnel transmission coefficient at that layer. So if we have an incoming ray and an outgoing ray, there's been some reflected ray, we need to know how much of this power was transmitted, how much was reflected. We find the product of all of these sort of transmitted power over incident powers, and find the product of those for all intermediate layers to know how much of the transmit power would have got through to our discrete target. We then calculate the reflection coefficient for the final interface that we're reflecting off of. We introduce a specularity. So when very rarely going to meet the ideal case that we have an incident ray and a refracted ray coming in exactly the same angle. So we need sort of the specularity coefficient here is I suppose in computer science you'd hear it called a reflectance function, or bidirectional reflectance function, and that's you provide a incident angle of your ray, you provide a reflected angle of your ray, and then it will give you a coefficient of the reflected power based on those two angles. So it allows for so again, we're not trying to find a exact incident and reflected response here, but we can also adjust this specularity coefficient. So to say if the layer was rougher, we'd expect a wider range of angles to reflect energy back at us. If it's a completely specular layer behaving sort of mirror-like, then we can make it act more strictly on this. We need the incident and reflected angle to be as close as possible to maximize the power that's being reflected. We have dielectric loss, which I have put down there, and the geometric loss. So that's just your sort of R squared spreading on the way on your transmission, R squared spreading on your reflection, and the product of both of those sort of geometric spreading, and two gains. So the first gain is the segment or line gain. So this comes from saying, well, we're not representing just a point target, we're trying to represent a length. We also know that physically our model would extend into the screen, into the model direction. So we calculate this rate, or this distance r, which is the additional sort of distance into the screen that a ray would travel within the same range bin. That gives us an illuminated area. We then calculate the sort of gain corresponding to the power that would be reflected if that area was the area that was illuminated. But the condition here then is that we're assuming that at least in R plus or minus into and out of the screen, for a model that the geometry is not changing. So that allows some sort of constraint of saying, okay, well, I know how wide I would expect my geometry to be constant in my model for this 2D approach to be valid. And then finally, we have a DRAMP game, which is that's added to represent the if there's a filter applied to the FMCW deramped signal, then we so that would be in effect a range dependent filter, because range is proportional to frequency. Then we're also able to apply a gain from that at that stage to derive the reflected power. So I'll now just go through these results. I'll try not to spend much time through them. But for all of these results, we're using a center frequency of 30 megahertz, bandwidth of 20 megahertz. Usually for the APIRs, we've been using a chirp duration of 1 second. Here the chirp duration is 12.5 milliseconds, because that corresponds with the equivalent chirp duration from the CST data that we've used. So I'll present results from our simulator that I've presented here, but also from the 3D electromagnetic simulator that and provide a sort of comparison between those results. So I've matched the chirp durations between those two. And we have a DRAM sampling frequency of 40 kilohertz and a transmit power of 0.1 watts. And then all of the back projections have been done in a constant velocity space of with a permittivity of 3.2. So this is our basal channel model. So we can sort of pick out along here, we have our base and our water conduit. We have our surface reflection up toward the top of the radiogram. And then on the right-hand side is the result from CST. So first of all, there's a bit of an amplitude mismatch between these two. That's something that I still need to identify the source of. So that's work ongoing. Potentially to do with normalizing the returned power from all of the point targets. And second of all, there's this. There is a slight shift in range between the two. That's consistent across all of the synthetic and CST models, or yes, the synthetic and validation models. And we can see here also these arcs on the side of each projected image are also brighter in the CST model. So to sort of explore why those arcs appear brighter, this is now looking at the raw range profiles for each radar position from left to right. So if we move from minus 40 meters in our model to plus 40 meters, the model was 100 meters in depth. So you see our sort of hyperbolic response that we'd expect from our channel. There's this sort of interference pattern that arises from our from the interaction between that hyperbola and the flat base of the bedrock. And then we have this secondary hyperbola, which corresponds to the reflection from within the conduit itself. And then if we compare this with the CST model, we can see that there's basically a much higher energy contribution and an extended range across all of the, so any range greater than 100 meters. So there are two factors that give rise to this. The first one is that in our CST model, we're actually simulating a 3D geometry. So we have something like this really badly drawn cube. So we have our conduit along the bottom, and we receive a bounce from the center of the conduit. But an effect of CST, using CST, is that we also receive quite a strong corner bounce. So in a previous presentation, I've been able to show that by changing the sort of width of the model, you can move this. Like I say, it would correspond to this interference pattern here, but you can move this sort of double bounce just by sort of increasing or decreasing what would be the in-screen depth of the model. So we're not changing sort of how wide the bedrock is in this direction. It's changing sort of into the screen how wide the 3D model is, and by doing that, we're able to see that we can move that, at least this sort of first reflection. So that I'm discounting, but obviously all of this additional stuff down here is still pretty significant compared to our synthetic model. And my assumption at the moment is this arises from the fact that with such a high dielectric contrast between the water at 80, 78 or so, and ice at 3.2, we see very strong reflections from the conduit at the base. So this leads to sort of a multiple, surface multiple, or not surface multiple, rather a bedrock multiple, and sort of scattering interaction between the sides of the conduit and the bedrock and back to the surface and so forth. So obviously that is an advantage of the 3D method, that we're able to simulate this sort of multiple scattering behavior, which at the moment we only account for one bounce per ray. We're not looking at sort of the effect of multiple bounces within the model. So if we sort of to draw this arc that roughly corresponds to any range greater than 90 meters or so, which is where the bedrock begins, then we're able to see that that's where this sort of bright reflection occurs. And if we compare that with the synthetic model, then that is where the power falls off from. So pretty confident that is a result of how we're back projecting these extended range profiles onto the sort of imaging space. And the reason that we don't see that in the center of the image is effectively they're cancelled out by complex summing of all of these back projections for each range profile. So at the center of the image, where most of these sort of arcs would overlay, that's where we're seeing the sort of effect of them being cancelled out, which is ultimately where you get the coherence gain in SAR from. So to be able to image a feature like this, in a survey design, we would need to account for saying, okay, we want to start so many 100 meters before the thing that we want to look at, finish so many 100 meters after, so that we can, without gating the range, then we can be sure that we're not going to have any of these smear to the left and right of our feature of interest. So that covers that. This is the phase. So these were amplitude plots in power. These are the phase plots. So what I've done is shift the phase based on the difference at the center of our, the center top of our conduit here. So I've compared those values, shifted the phase response accordingly, and we can see that, broadly speaking, the phase response is comparable. There's this range shift that I've mentioned between the two models. But broadly, this approach with the point targets is giving us the right right looking data that's a reasonable representation of a much more complex simulation space with the 3D model. So that's sort of to provide some confidence. To validate our zero height code, I just went back and did this with the Basal step models. So here we have a Basal step using the zero height, synthetic, and CST approach. Sorry, this is our previous approach without zero height spaces. So neither of them have zero height elements, but just to check that if there's nothing that's zero height in it, everything's still work okay. And we can see that they're all pretty comparable. There's again this amplitude mismatch that I've not yet got around to correcting. I'm not too concerned now about the amplitude mismatch from this previous code, as that's old code, but mismatch between the zero height and CST stuff still needs to be corrected. So if we look at the raw range profiles again, this is the sort of corner bounce response that I was talking about, but there is sort of additional sort of this sort of spurious behaviour here that's perhaps as a result of multiple bounces that would be nice to see if we can include by introducing multiple bounces into the synthetic approach. But this sort of dominant secondary bounce comes from that sort of corner bouncing effect that we get from, if we have some geometry down the middle of the model, then we also see a strong bounce from each corner as well. Again, comparing the phase between each of those models, and then we have just another model geometry there, but pretty much more of the same thing. How does it perform computationally? Well, the CST, so the full 3D electromagnetic models, they take about 80 minutes to run one, or to compute one profile. So that's one strip of the of these sort of raw images here. So 18 minutes for one strip of those, compared to 1 second for the previous model. And with this zero height adaptations, it takes about 4 seconds. Obviously, if you start making the models more complex, that time per simulation is going to go up. But I think we do have, within this sort of ratio of 1 to 10 to the 3, we have room to improve. We have room to allow for that increased computation time, with that still running below what we're seeing with CST. But with CST, we are getting these secondary, tertiary bounces and sort of more faithful diffraction effects from the base as well. The other thing there is that these CST results were conducted on sort of a 3 GPU high performance computing cluster. I've done all of the synthetic simulations on my own PC. So practical use of this software could be, even when you're in the field, you're able to knock up a simulation, check whether this matches the data that you're seeing, and allows for almost in electronics, I guess, the equivalent of sort of a rapid prototyping approach, or almost a rapid modeling approach. So you're right, does this make sense? Is this what we're expecting? So having this reduced complexity could be a useful thing in multiple scenarios. So where are we going with this? There's a reasonable agreement between the two, and they run faster, so that's always nice to see. But the multiple bounces are something that I think would be a nice feature to introduce into our synthetic simulations, particularly because they crop up time and time again in real radar surveys of ice shelves. We see very strong reflections, and we see these sort of surface or basal multiples, but because ice is relatively low loss, they show up brightly. So they are a feature that someone trained in looking at radiograms of glaciers would expect to see. The second thing that would be nice to look at is sort of the introduction of discrete clutter. So whether there's a water inclusion in the ice, if there's something that we want to be able to represent, but a zero height layer isn't a faithful way of doing that, then can we introduce sort of actual point scatterers as well? It's not to try and represent this kind of coherent noise that we get from clutter, rather than sort of we can't just add an additive Gaussian noise or something like that on top, because it will be integrated out throughout the back projection process. So we need a way of introducing this coherent noise into the model, again, to sort of represent those effects that we see in real radar. I've mentioned there that something I'd like to investigate using a shooting and bouncing style approach. At the moment, I'd sort of describe this more as a Huygens approach, that we're looking at each of these responses and then spreading the wave spherically or cylindrically from each of those responses, and summing the to find the phase of the wavefront back at the receiver. So if we shoot the rays through our aperture, more similar to sort of optical kind of ray tracing, then do we get different results? Are the results still useful? The reason at the moment for going behind this Huygens approach was that we might be able to, if there are sharp changes between these sort of zero height objects like the basal conduit or something like that, then we might be able to more faithfully represent some of the interference and diffraction effects that occur in that space with a sharp change in the geometry. So I think it's pretty much that done. So if there are any questions, I'd be more than happy to take them. Thanks for putting up with talking through that so quickly.